Different types of explainability metrics. In the realm of artificial intelligence and machine learning, it is crucial to have models that are not only accurate and efficient, but also interpretable and explainable. The ability to understand and interpret the inner workings of a model is essential for building trust and deploying AI applications in critical domains such as healthcare, finance, and law. To assess and quantify the explainability of AI models, various explainability metrics have been developed. These metrics serve as quantitative measures to evaluate the transparency and interpretability of models. In this part of the course, we will explore different types of explainability metrics commonly used in the AI community. Feature importance is a widely used explainability metric that aims to identify and quantify the contribution of individual features or variables in a model's decision-making process. There are several techniques to calculate feature importance, such as permutation importance, SHAP values, and information gain. These metrics provide insights into which features are most influential in determining the model's predictions. Model complexity refers to the intricacy and sophistication of a machine learning model. It plays a crucial role in explainability, as simpler models are generally easier to interpret. Metrics like the number of parameters, depth of the model, or the degree of nonlinearity can provide a measure of model complexity. A higher complexity may indicate a more challenging model to understand and explain. Rule-based metrics assess the model's interpretability based on the existence of explicit rules or decision paths. These metrics aim to quantify the transparency and comprehensibility of the underlying decision-making process. Examples of rule-based metrics include the number of logical rules, rule length, and number of conditions for decision paths. Rule coverage measures the proportion of data instances that are correctly classified by the model's rules or decision paths. It reflects the model's ability to capture and explain the majority of the data distribution. High rule coverage indicates a more robust model with a better understanding of the underlying patterns in the data. Model distillation metrics evaluate the quality of a simplified or distilled model against the original complex model. These metrics compare the predictions and decision boundaries of the two models to assess if the simplified model captures the essence of the original model's behavior. Metrics like accuracy, precision, recall, or FON score can be used to measure the performance of the distilled model. Local explanations focus on explaining individual predictions rather than the entire model. Metrics such as LIME, local interpretable model agnostic explanations, and SHAP, Shapley additive explanations, provide local instance-level interpretability. These metrics highlight the features that influence a particular prediction, enabling users to understand why the model made a specific decision. Transparency metrics assess the comprehensibility and understandability of a model's underlying algorithms and decision-making process. These metrics aim to capture aspects like code complexity, algorithmic transparency, and documentation availability. They provide an overall measure of how easily a model can be audited, reviewed, and understood by humans. In conclusion, explainability metrics are essential for assessing the interpretability of AI models. They allow us to understand how a model arrives at its decisions and provide insights into the underlying factors driving those decisions. The incorporation of these metrics into model evaluation frameworks enables more transparent and explainable AI systems.